it makes me think about many conversations I've had over the years with my colleague Ted Jabal, and in particular, he liked talking to theorists, but he very much had this opinion that if we really think we've understood something, then we should do something useful, which is to give new directions for finding new superconductors. So just the purpose of this group here. Wrong direction. So I'm going to start with provocative things and then get more and more crazy as we go. So let me start with a proposal for how to make high TC in the cuprates higher in the context of the cuprates. So building on things that I think, at least I have some understanding of. And then I will discuss an idea, again, an old idea of a kinetic energy-driven mechanism of superconductivity being important here. And then I'll, as I said, move further afield, at least by my standards, sort of crazy, but something that an idea we had called the spin gap proximity effect, which I will try to explain. Okay, so let me start with the properties that we think we know about the cuprates. And so there's a phase diagram of the cuprates where there's a superconducting dome. And there was a perspective on this dome that Vic Emery and I put forward. Many other people had similar ideas, which is that there was a crossover at optimal, well, there's a superconducting dome, of course, that we knew, but that there was, a crossover between a low doping regime where TC was going to be determined by phase ordering, so T theta is the phase ordering temperature as estimated from the zero temperature superfluid density, and an overdoped regime, which was going to be much more BCS-like, where TC was determined within BCS mean field theory by the magnitude of the superconducting gap. So a long time has passed since this. Some of this is really clearly correct. You can measure the superconducting gap scale. Its magnitude is large compared to you can measure that by, gaps don't come with names on them, but if you measure the near antinodal gap, you're sure you're measuring a superconducting gap. And so from the slope near the antinode, what? Near nodal gap, you know you're measuring a superconducting gap. This is measured at low temperature, and you can see that indeed the gap is large compared to TC in the underdoped regime and doesn't have the same trends with doping as TC does. So that's as expected, and it drops and gets to be relatively close to the expected magnitude as you go onto the overdoped side. So that turns out to be okay. You also do see evidence of gaps that open up above TC. That's what pseudo gap meant here. It's a little bit less clear which of these are superconducting gaps, but even over here, for instance, Yuhei has shown data that show that there's a particle hole symmetric piece of the gap that opens up somewhat above TC. So this picture, that part of this picture doesn't look so bad. And I should say it's a completely separate question about whether T star and all of the pseudo-gap phenomena seen above TC are related to superconductivity or to other things. This is just talking about the superconducting component of whatever gap we're looking at. Okay, so that's good. So the pairing scale is not what determines TC in the underdoped regime. The pairing scale is such that you might have expected to get a much higher TC were it not for phase fluctuations. Now, the superfluid density turns out not to do what we expected. The superfluid density does sort of track with TC on the underdoped side, so that's fine. That's consistent with TC being determined by phase ordering. But many experiments now show that it also drops with TC on the overdoped side. And so TC again has a significant contribution from phase fluctuations, and the phase stiffness becomes really small on the overdoped side. So that's unfortunate. If that's true, the next things I'm going to describe are not true. So what I want to do is to conjecture that this experiment, while correct, is misleading, that the drop in the superfluid density on the overdoped side is a consequence of disorder. We've carried out calculations to at least show that this is plausible, that you get sort of self-organized granularity over here, which was responsible for a big suppression of the superfluid density. So what I'm going to do is to imagine that the cartoon, or here's an updated cartoon in a recent perspective that was posted recently by Brad Ramshaw and me. So this is what my claim is, that the phase diagram of a clean, disorder-free cuprate would look like. And there are many things about this. If there's time in the discussion, I would be happy to tell you the motivations behind this and some of the implications. But for present purposes, the only thing that I want you to take away from this is that there is reason to at least conjecture that the original idea that TC is bounded by phase ordering on the underdoped side, but is bounded by pairing on the overdoped side, and that the superfluid density on the overdoped side is intrinsically large. That's what I'm going to assume from now on. Okay, so this then brings me to, again, not a new, but a newly interesting proposal for how to make TC higher. So the underdoped cuprates are not a higher temperature superconductor because they have low superfluid density. The overdoped cuprates have a high superfluid density, but a low pairing scale. Could we imagine combining these and inherit the best of both worlds? So that's the idea. And with Erez and Dror, we carried out some calculations. We said, let's consider a model problem where we have one layer that has a big pairing scale but very low superfluid density. Let's have another layer that has a small pairing scale but a large superfluid density. And then let's turn on some weak tunneling between them, and let's see what we get in the terms of superconductivity from this. And so to have a problem that seemed relatively simple, we took for the red layer to be a negative U Hubbard model with a really big negative U. So the superfluid density would be near 0. In fact, I think in some cases we set T equal to 0, so the superfluid density in this layer was 0. In this layer, we're going to have T much bigger than U. I think we set it equal to 0 to be simple. All right, I had this inequality wrong. That's supposed to be greater than or equal to. And then we used various crude approximated methods to solve this. We calculate the mean field TC, and that drops as you turn up T perpendicular. And that's the inverse proximity effect. The BCS, mean field theory, on this negative U sites gives you a perfectly good TC on the order of U. And then as the electrons spend less and less time on the layer with the attractive interaction, the mean field TC drops monotonically with T perpendicular. But then we estimated what would be the actual TC by computing the zero temperature superfluid density and then asking when does the superfluid density equal TC, and that gave us this curve that first rises. That's due to the proximity effect, and then so inducing superconductivity in the metallic layer, and then the inverse proximity effect as the mean field TC drops. So it's two versions of the proximity effect working against each other, but it says that there is an optimal coupling between these at which maybe you could get a very high TC. More recently, there have been the negative U Hubbard model can be solved by sign-free quantum Monte Carlo calculations, which was done by these gentlemen. They didn't take quite as extreme parameters as we did, but if you, for instance, look at this blue curve, which is for U equals -10 on this layer and 0 on this layer, you can see that as you turn up T perpendicular, you actually get, indeed, an optimal value at which TC is maximized. So in theory land, at least, this idea works. So now let me try to present some experimental evidence that this is not just a theorist's fantasy. So how would we check this in the cuprate context? So the best way to do it, which hasn't been done, would be the following: to take a bilayer cuprate, and the bilayer cuprate, all the ones that we typically study have a mirror plane, and therefore the doping concentration in the upper layer and the lower layer are equal to each other. But if we were to break that symmetry, either by having asymmetric charge reservoir layers above and below, or learning from our 2D colleagues by putting on a big displacement field, then we could imagine a situation where we would separately be able to tune the doping on the upper and lower layer and arrange ourselves so that one of them was overdoped and one of them was underdoped. And then we would explore a new branch, a new avenue, dimension of the cuprate phase diagram. We could imagine a phase diagram with two doping concentrations, X1 and X2. And we could ask, what is TC as a function of X1 and X2 in this bigger space? What's been explored up till now is mostly along this line. And what we know is that there's some optimal TC here. There's a lower doping at which TC vanishes. There's an upper doping at which TC vanishes. But then the question is this an absolute maximum? That is to say, is this the top of a mountain? And as you move off, I mean, it must be symmetric as I move off of here, but it could be a mountaintop like this, or it could be a saddle point like that. And if it's a saddle point like that, then somewhere out here, we would find the optimal TC in this two-dimensional phase diagram, which could be substantially bigger than the optimal TC we found so far. So that's just on, functional analysis. These are the two possibilities with a 50-50 chance of one or the other. But with the motivation that I've just described, we might think that it's a good chance that this is the case that applies. Okay, so that experiment hasn't been done, but there are very suggestive experimental results from tri-layer BISCO. So tri-layer BISCO looks like this. There's the charge reservoir layers, and then there's 3 copper oxide layers. And the inner layer and the outer layer are crystallographically inequivalent to each other, which means that for sure the outer planes and the inner planes will have different doping concentrations. So this is the sort of situation that we're interested in. And because the charge comes from the charge reservoir layers, in fact, what we expect is the outer layers will be more heavily doped than the inner layers. So this is the sort of situation that we might hope this physics plays out in. So let me look at this same thing, not from a real space perspective, but from a band perspective. Fortunately, experiments have been done on this. And what you see is, as you would expect, you see 3 bands. There's an alpha band, which is on the outer planes, and it has anti-bonding symmetry. That is to say, it's odd under reflection through the mirror plane. So this band has actually no amplitude on the inner plane at all. Then there's 2 symmetric bands. There is the beta band, which is primarily on the outer plane, and the gamma band that's mostly on the inner plane. And if you're optimistic, you might think that this problem actually maps onto the 2-plane problem that I was just discussing, that the alpha band maybe is decoupled from the physics here. And so we can think of this as the outer planes being represented by the beta band and the inner plane being represented by the gamma band. There's another peculiarity of tri-layer BISCO, which is that there isn't a TC dome. So here's TC as a function of doping. Actually, it's here, rather than saying doping, which is always a little bit negotiable in these things, they plot directly the C-axis lattice constant, which is thought to vary linearly with doping. So these are all experimental curves. And here's the familiar dome for bismuth 2212. The TCs are scaled by the optimal TC, which is why they intersect here. The tri-layer BISCO has a higher optimal TC. But what you see is that the tri-layer BISCO has this peculiarity. The TC rises to optimal and then stays almost constant as you move into the overdoped region. And that's a notable thing that we would like to understand as well. Yeah, it's where the resistance is 0.
Distance. It's not tunneling. It's not ARPES.
No, this is resistance.
Okay. And
on these curves, this is resistance.
Okay.
And these are bulk samples. The ARPES are not on bulk samples, so I'm comparing. Okay. Ask me about exactly what the samples are on the ARPES. I'll tell you. But anyway, this is resistance measurements and magnetization too. This is real. Well, so as you'll see, this TC is higher than any single layer or bilayer person here. So this, the optimal TC in tri-layer BISCO is 110 Kelvin. Okay. And they're coupled to each other. They're not decoupled. So, and they measure resistance both in the A, B, and C directions. So there's nothing wonky about this. This is really bulk materials.
How is it bulk? I mean.
No. This is, the crystal structure has repeat structures like this.
Oh, okay.
This is the unit cell.
Oh, it's just the unit cell.
That's the unit cell.
Okay, so it was not gates. It's just.
No. This is doping. Yeah. These are bulk crystals.
Oh, then it's just misunderstanding. Okay.
So what's the charge reservoir?
Bismuth oxide. I don't know. It's complicated. And by the way, these materials actually aren't crystals. So there's really, although I'm showing you ARPES and a Brillouin zone, they have an incommensurate superlattice modulation. So these aren't even crystals. They're quasi-crystals or something like that.
That's an abusive term.
What?
That's an abuse of the term quasi-crystal.
They're quasi-periodic.
That's fine.
Okay. So So going back to this picture, this is an ARPAS picture. And what you can see from ARPAS is you can estimate the area enclosed by the Fermi surface. So we don't have to guess. We can tell what is the doped hole concentration in each of these bands. And that's what's plotted here. So this is for two different samples. The squares are for optimally doped trilayer bisco. And so what you can see is that the gamma band has an extremely low concentration. It's about 6%. So by itself, this would have a TC that was near 0 because it's too underdoped. And the beta band has a very high doping concentration, about 26%, which again would have a TC by itself that would be close to 0 because it's too overdoped. And the alpha band also, it turns out that in the optimally doped, you can't separate the alpha and beta bands. So within experimental error, they have the same doping concentration. And then the red dots are more recent data on an overdoped sample. And what you see is that the extra doping has gone entirely into the alpha band. And so the first thing that we understand is that indeed the saturation of TC is not so unexpected from the proposition that the alpha band is decoupled from the physics. So the high TC here is really a function of the coupling between this very underdoped and very overdoped band. And the TC is 110 Kelvin, so it's 15 Kelvin or something higher than optimal in the bilayer bisco. Okay, so if you believe this argument, then what we've seen is that somewhere out here and here, we have a TC that's higher than the highest TC here. No reason to think that this has found the absolute maximum here. So I think the first experiment that I suggested, where we tune this doping with a gate, with a displacement field, is something that should really be done. Oh, wait, I don't need this. I mean, no, of course it's a different material, but they're as similar as you can get. The charge reservoir layers are the same. The outer planes are the same. The inner plane is different in that the inner plane has no apical oxygens. So there is something else different. But we've sort of come to accept that TCs are fairly robust. The bilayer in YBCO and the bilayer in BISCO are very different from each other, and yet the TCs are very comparable. So, it's not a theorem, but experience tells us that we should probably take this seriously.
Case for Ivan Bozovic or similar people who could really design your original bilayer with different things on different sides. So was that ever attempted?
Yeah. So Ivan Bozovic did exactly that. He took an undoped lanthanum cuprate, highly overdoped, 30-some-odd% overdoped lanthanum strontium copper oxide, made a sandwich of them, and found that TC went up to 42 Kelvin. Okay, that's great. I would love to declare victory. The problem is that LSCO's highest TC is 38 Kelvin, but LSCO under expansive strain can be, it was 52 Kelvin, but LSCO under, that's what Ivan found in this case, but LSCO under expansive strain can be raised to 52 Kelvin. So it was a correct prediction. It was a prediction. It was correct. But whether it was right for the right reason or right for a completely extraneous reason is unclear. Okay, yeah.
So I like this understanding because it's very consistent with the interview you showed us. But how do you explain the 4-layer, 5-layer, and so on? Because you can keep going on,
Yeah.
isn't it? More layers.
Yeah.
So eventually TC drops.
No, so look, once you get to 4-layer and 5-layer, you get insulating behavior. Well, you don't have insulating, but you have antiferromagnetism in the inner layers. It becomes much more like, I think you said, just that it's the outer layers that are being superconducting, maybe with still some help from the inner layers, but this one's optimal in the sense that we really still have substantial doping on the inner plane, and we don't have antiferromagnetism. I don't know for sure that antiferromagnetism is a problem, but it might be. Yeah. Yeah, that doesn't work because the interbilayer tunneling is so small that it can't make any difference on TC. What we need is couplings between the systems that's of order the gap. That's what's optimal. Okay, so my proposal of a single bilayer of BISCO with a displacement field is the perfect test of this. Okay, let me talk about kinetic energy versus potential energy-driven mechanisms of superconductivity. How much time do I have? 30 minutes, okay. So I'm going to finesse some issues of definition of what kinetic energy and potential energy means, so don't worry. It'll be in a very physical sense that I'm talking about. And so, in the weak coupling limit, the normal theory of superconductivity is definitely potential energy driven for the very simple reason that the ground state of the metal is the ground state of the kinetic energy. So any change you make in the state costs you kinetic energy, so it better gain you attractive energy, potential energy of interaction between the electrons in one way or another. In strongly correlated fluids, the normal state is a mess. It's got strong correlation effects. So you could imagine changing the sign of this effect. Let me give you a very simple model where you can see something like this happen. Let's consider the Hubbard square. And of course, I can't consider superconductivity, but I can consider pair binding. So what I'm going to do is you calculate the ground state energy of this square as a function of the number of electrons, or Q, which is the number of holes. You can do it analytically. And then I'm going to calculate the pair binding energy, which is to say, if I take 2 squares, each of which have 4 electrons on them, and then I remove 2 electrons from the system or add 2 holes, is it better to take 2 from one square and none from the other, or 1 from each of the 2 squares? So that's if E0 plus E2 is smaller than twice E1, it means you would prefer to have 2 electrons on the same square. And here's what you get for the pair binding energy. You find that there is pair binding for U small. You can calculate it within second order perturbation theory. Then there's a critical value of U at which it goes away. So there's some intermediate value of U where you get pair binding out of just the simple Hubbard model. And that's very nice. But you can also ask, is it the potential energy or the kinetic energy that's gained by the pair when we form this pair binding? And since the potential energy by the Hellman-Feynman theorem is just U times dE du, what you can see is that the potential energy of pair binding changes sign at this minimum. So on this side, the pair binding is potential energy driven. And on this side, the pair binding is kinetic energy driven. Okay, now I want to consider a more physical case of kinetic energy driven pairing, and that's the proximity effect, which obviously was important to my earlier study, but now we're going to look at it again. So suppose I had a system that consisted of a mixture of metal and superconductor, but suppose I put infinite barriers between the metal and the superconductor. So then, although locally I will get superconducting pairing in the superconductors, globally this thing is either an insulator if the metal doesn't percolate, or a metal if the metal percolates, but it's certainly not a superconductor. And now what I'm going to do is I'm going to remove the insulating barriers and allow electrons to diffuse between the metal and the superconductor. And then I know what will happen is that by the proximity effect, I will induce superconductivity in the metal, so this thing will become some array of SNS junctions, and it will superconduct. The metal was in its ground state before I removed this, so the energy in the metal has gone up in this new state. The energy in the superconductor has also gone up, but not much, since only the edge of the superconductor is affected. So what is the gain in energy? The gain in energy is that the electrons pair up in the metal so that they can delocalize across the superconductor to metal barrier. So the kinetic energy we gain is pair delocalization between the metal and the superconductor. So this, is well-known physics, but it's an example of a kinetic energy-driven mechanism of superconductivity.
So there should be some mechanisms giving superconductivity in the first place.
Yeah, so there is, but the thing that drives this system from an insulator or a metal state, so if I look at it as a statistical mechanic or a thermodynamics person, and I ask, what is the phase of matter? I've started with an insulator, or I've started with a metal, and then I allow the system to lower its kinetic energy, and that's what's driven it into a superconducting state. So, this may be a semantic issue, but definitely in going from the decoupled superconductors to the proximity effect, so looking at it from the metal point of view, the only thing that the metal has to gain from this is kinetic energy of delocalization.
But Steve, you said thermodynamic, and thermodynamically it's mixed phase.
No, it isn't. This is a superconductor. Thermodynamically, I don't see the size.
No, but particularly the metals and the insulators, the mixed phase.
No, Paul, you're wrong. But we can discuss it later. But I need to finish. But this is by thermodynamics. You're just talking about macroscopic measurements. Okay. So let me show you how this works in real superconductors. Here are some beautiful old experiments of Bob Dines, where he took granular lead and then deposited increasing amounts of silver on top of this. Silver is a normal metal, and it also wets. And so in the normal state, the resistance drops smoothly with silver. There's a complicated evolution of the resistance. You can see that something happens at the bulk TC of lead, at least until you get a lot of silver coming on it, and then you're inducing superconductivity in the system. What's going on? Oh, and also you can measure the gap in these by planar tunneling, and what you see is that the gap as you put on silver first doesn't change and then starts to drop as you put on more and more silver. You can look at, just as we would in the Cuprates, you can look at 2 delta over Tc. Here, Tc is defined as the temperature at which the resistance has dropped to half of its normal state value. It's not a real Tc. It's some sort of practical metric. But you see that the gap starts big and drops down to a sort of a BCS value. That's the inverse proximity effect. The gap is getting smaller and smaller as you put on the silver. But on the other hand, what you can see is long before that, you're getting a lot of superconductivity. This is, I should stress, a log plot. So this is many orders of magnitude drops of resistivity. And so they drew this phase diagram, which of course looks alarmingly like the phase diagram I drew at the beginning, except here it's silver coverage on this axis. And again, you see a crossover from where the silver produces more Josephson coupling, so helps with phase stiffness, to a region where silver hurts by the inverse proximity effect. Okay, so now let me go beyond Andre's objection. So what we proposed is something even more crazy than this. So suppose now I again consider my two-component system, of which one is a metal and the other is something that's paired, but it's a paired insulator. So I want to have an insulator, but still with some effective negative U, so the energy to add 2 electrons is low compared to twice the energy to add 1 electron. And now I'm going to allow tunneling between these, and my claim is that under some circumstances, the metal will pair up so that it is easier for the electron pairs to delocalize between the paired insulator and the metal. We, in this paper, which is long and very technical, I'm afraid, we worked out the example of a 2-leg Hubbard ladder at half filling, which is an insulator, coupled to a single-leg Hubbard chain, and we showed that for the right range of parameters, we could get a big superconducting response from this mechanism. So here's my crazy proposal to you guys. Look for paired weak insulators. They have to be weak because if it costs too much energy to tunnel a pair into them, it doesn't do us much good. And couple it to a thin layer of metal. I have in mind some things that I happen to know. People have reasons to think there may be some pairing in the insulating state. And okay, so let me just summarize my talk. So first place, I think superconductivity is always a crossover phenomenon. It's not something that you can find in the limit that some interaction goes to infinity or something like that. It's always an intermediate thing, so you're always going to be fighting these battles. The main idea I want to sell here is that because of this, we may do better in multi-component systems, one component that's optimized to solve the pairing problem, and another one that's optimized to give you optimal phase rigidity. And then the really complicated thing is that you need to be able to have coherent pair tunneling between these two systems on a scale that's not too big so it doesn't destroy the gap, and not too small because you do need to induce some superfluid rigidity. So thank you.
Thank you, Steve. Questions?
Sorry. Yeah, go ahead. Yeah. Mhm. There's been a lot of talk recently in the context of Moiré systems about lightly doped triangular lattice antiferromagnets from people like Atak Imamoglu and Eugene Demler in Zurich. Do you have any comments on those systems?
So, okay, so I don't know about the work, but the definite, we're always dealing with effective models at low energy. And the downfolding from some microscopic model mixes kinetic and potential energy. In some sense, it's an accounting issue. in the cases I was doing here, it isn't. It's really clearly that it's the energy to delocalize the electrons from one thing to another. But in the other case, I mean, the fact that you can get superconductivity in flat bands shows you how complicated the accounting issue is.
Oh, no, that's all true, but what's in their mind is really something much closer to Anderson's original picture, that you start with something which is in effect a correlated insulator, and then you get various kinetic-driven phenomena.
So this is also like Jorge Hirsch's idea that
it
a
goes
pair
back
of,
to that.
Yeah.
It goes back. It's a cousin of that anyway.
Yeah. I don't know. It's an appealing intuition when, in the old days, when people tried to make it work, there were all sorts of problems with it. It didn't work. I don't know.
That's their claim is basically you have these systems that does work, and the further thought is you can put them in proximity to other stuff. So it might be an
Okay.
application for what.
Yeah.
To see a sizable effect? And do you think it's possible in a device to really induce such a huge density difference?
So I've talked to people. So first place, I would be happy getting the sign of the effect right. So if they can induce this asymmetry and see a 1 degree increase in TC, I'm prepared to declare victory. I have low standards. But if we go by the tri-layer BISCO, that we want something that's comparable to the full width of the dome, then that's at the edge of doable. That's higher densities than typically are done in the 2D materials, but people I've talked to, like Philip Kim, thinks that certainly several % doping is possible. That doesn't mean it's easy, but I think the range of dopings are, okay, it's at the edge of what's possible, but it's doable. Probably better to do it by having asymmetric charge reservoir layers, but okay, both. I like the gating because it's controllable.
Continuous, yeah.
Layers with different reservoirs. There may be inspiration from the iron arsenides in the calcium, potassium, iron 4, arsenic 4. It's basically a alternation of 1, 2, 2s, and you could get it crystallographically because you had very different C-axis contrast and in-plane rastering. So it's conceivable that you may be able to, that clever chemists may be able to get a bulk crystal that manifests this. There's enough of a menu to choose from that might be worth looking at. That's the comment.
Yeah.
The question, can you go back to your silver and lead picture? Because I am often wrong, but I would like to understand how I'm wrong.
I think 6.
42 is my preferred, but okay, good. So what's the size of the lead? Is it?
They're about 50 angstrom. Typical grain size is 50 angstroms.
So that's big enough to be superconducting?
Yes.
Then the lead is always superconducting.
So it's
Yes?
an interesting limit. So the lead is big enough to be superconducting in an insulating matrix.
Right.
But in a metallic matrix, it's too small to be superconducting.
So your TC, is that not the experimental TC, is that a transport TC?
So everything here is from this curve. So this is the experimental data.
Right, so it's transport.
Yes.
Right, what I'm still struggling with, because if you go back to your schematic.
So let me just point out something here. So you can see here, as you first put on silver, here I've still see a deflection at the bulk TC of lead, and then I see phase fluctuations, quantum phase fluctuations. I mean, who the hell knows, but the resistance is dropped by 5 orders of magnitude, so it's superconductivity of some sort. But the scale of onset is set just by the superconductivity in the lead grain. But here, as I've got more silver on it, nothing happens down to a temperature that's way below so you
Sure,
can see
but-
the suppression.
But then in the one you described earlier, we would describe that as mixed phase. You have superconducting lead, and then you have silver on top.
No, mixed phase means macroscopic mixture of two phases. To me, thermodynamically, mixed phase is like when you have phase separation, you have macroscopic things. These are not macroscopic. This is, 50 angstroms. That's a microscopic length scale.
So in your schematic of blocks, you're again having an inherent 50 angstrom concept.
Yeah, or
Okay, because at a certain point it becomes mixed phase, and it's just a question of what size you're talking about.
Correct.
Okay, I just wanted to understand. Very good, thank you.
Yeah. About your first comment,
Yeah.
the Cuprates, I'm quite confident in the underdoped regime are in this regime where pairing is large and phase fluctuations are what govern TC. I'm less certain that the iron-based superconductors ever get into that
Oh, no,
regime.
no. We can take inspiration crystallographically. It was very interesting to have 122s that if you don't have this contrast and epitaxy alloy, but if you have enough contrast and epitaxy, they form a true quaternary that has different layers. And that's what you're after.
No, but I'm after, I'm
No,
after.
in cuprates, you might be able to find a similar recipe to get to that in cuprates.
Oh, okay, yeah.
No,
So
that's the inspiration.
Okay, so there is such a material. There's YBCO 347 or something like that. It's got YBCO, cuprate copper oxygen bilayers, then single chain layer, bilayer, and then double chain layer.
Okay.
So it's sort of halfway between 123 and 248, and that does have unequal dopings. And under a little bit of pressure, it also goes up to 110 Kelvin. But it's also got lots of other differences. Again, I'm not sure I'm
Not
prepared.
as clean. Yeah, understood.
Okay, let me ask you one question just for entertaining purposes. This is about kinetic energy-driven mechanism. So, as you know very well, a number of years ago, a number of people were basically saying this. Consider strong coupled superconductor from general physics perspective. This is a system which has a lot of incoherence. In the normal state, you go into superconducting state, you clear fermions, they become coherent, and you calculate change of kinetic energy, you get gain of kinetic energy.
Right.
Mechanism is still underlying pretty much the same as weak at strong coupling, but you calculate feedback from superconductivity. So will it be, in your language, also kinetic energy-driven mechanism?
I mean, I don't know. At some stage, these become semantic questions. Certainly this interlayer tunneling mechanism that Anderson and Chakravarty proposed, which is clearly not operational in the cuprates, but it was in this same body, and again, it was similar in structure to that. I don't know. I don't have a.
More questions? Yes. Go ahead.
So it seems like the theory that you mostly focused on was the theory that's far away from the saddle, right? You take an undoped and right. But now, if you had an ab initio or some other sort of a reliable numerical method in the spirit of, again, Hellman-Feynman theorem, what controls the coefficient of the delta x squared? Like, is this something that one can just go and map out for lots and lots of materials and try to figure out how to?
Well, that was sort of my answer over there. I mean, my argument for this is my theoretical argument is qualitative. My only quantitative estimate comes from 2 points that are far out. So I assume the curvature is something like the distance to those.
I guess I'm saying, in the spirit of a linear response, what experiment does one do to figure out there should be a light scattering,
Okay, look, it depends on how optimistic you want me to be. These photo-induced superconductivity states in YBCO, which half of the people I talk to say aren't light-induced superconductivity and half say they are. So let's put that on hold for a second. But what they are done is they're driven by driving the apical oxygen up and down. And what you can see is if you look at that from this bilayer, that when the oxygens go like this layer gets more doped and this layer gets less doped. So they are oscillating precisely the asymmetry that I think is a potential big lever. So, okay, I can take optimism from that.
There's nothing on the trilayer of this.
No.
One question from here also. Okay, sorry. Yeah, let's go.
Very quickly, I was wondering what the implications are for a possible second superconducting dome with higher doping in the
So that was certainly Ted Jabal's favorite topic. I don't know, it's a really interesting idea. None of the data is completely compelling and none of it is easily dismissed either. So yeah, I don't know.
Yeah, go ahead.
Ignore the question. So you basically want large superfluid stiffness for one material and large gap for the other layer. Is it clear that the largest superfluid stiffness in nature is in a cuprate?
No, it isn't.
Known to us.
No. Of course, the cuprates. The reason it's obvious that phase fluctuations are important in the cuprates is they've got lower electron density. They're larger RS to start with, or something, than almost any metal.
So why does the bilayer need to be two cuprate layers?
It doesn't. It would be better to have it be, silver or something. But the problem is that there are many moving parts in this. We have to also put them in good proximity and ensure that we have coherent tunneling between them on a scale that's of order the gap. And if you put two dissimilar materials together, they tend to just not talk to each other. So, I mean, you're right, there could be much better choices of the metal than an overdoped cuprate.
So, but I understand the about raising TC while keeping large electron density, right? But also, I think that from Diane's paper, where on the horizontal axis there was this parameter ds plus dn over something, right?
Right.
So I think that was basically that whole theory of proximity.
That's absolutely just the Cooper limit. So so here, that's correct. So that's what I said. So that's what the physics is of the dependence on T perpendicular. So if we take our gapped superconductor and our metal, and we turn on a T perpendicular, the first thing we do when T perpendicular is small compared to the gap is we induce superconductivity in the metal. So that's analogous to what's happening here. We get strong Josephson coupling through the SNS junction without suppressing the superconductivity on the grain. Then when T perpendicular gets to be big compared to the gap, then we get the inverse proximity effect, which kills us. So this is the hard piece of tuning. The T perpendicular should be of order the gap. If it's much smaller than the gap, we get nothing. If it's much bigger than the gap, we destroy everything. So this is only true in the Cooper limit. So this is not happening here. So roughly, it's a self-consistent thing. So when you get a small TC, then your coherence length has gotten larger. If your coherence length is large enough that you're not getting superconductivity within the grain, then you have a uniform superconducting state. So the Cooper limit is assuming the superconducting order parameter is uniform. Right. And so when you have very little silver, the superconducting order parameter is very non-uniform. It's much bigger in the lead grains and much smaller in the metallic regions between the grains. Once the silver gets to be enough, you go into this homogeneous superconducting phase. Just for those who don't know, basically what this says is that if the electrons are delocalized between the silver and the lead, then it feels an attractive interaction only for the fraction of time that it's in the lead. So lambda gets scaled by the fraction of the system that's lead. And that physics is very simple in the Cooper limit. So I have to stay away from that limit, and I also have to stay away from the limit where the coupling between the systems is too small. So we have a narrow window that we have to aim for.
So just like two materials in proximity. But at the conceptual level, this sounds like some kind of heavy fermion thing, that it could be just one material with two components. So can you comment which one you think is kind of more promising?
So, so we thought about, I mean, you can think about negative U centers, which were going to give you a charge condo effect. So they've got big pairing. They have two states that are near the Fermi energy, either with 2 electrons or 0 electrons on them. And so that's a sort of a version of this, that you have the strong pairing system there, you have your itinerant metal, and then you couple them together. And there's some evidence, for instance, that that's responsible for the unusually high TC in lead-doped mercury telluride. Yeah, lead-doped mercury telluride. This is, again, Tedjabal and Yorick Schmalian have worked this out. It's not as good as it could be, because the main thing that it's inclined to do is the condo effect. And so the impurity goes away in the condo effect, and it just makes your metal a heavy metal of some sort. So you have to find a way of keeping it from doing the condo effect and instead do this. So, you know, I mean, it's in the same family of ideas. All of these ideas require threading some needle. So one should probably look at that. But at any rate, when we looked at it before, we decided that that was probably not going to work all that well because of this.
In the last 30 seconds, let me ask the last question. When you talk about this increase of TC, you basically talk about limits when the layers are very different. Now you take your model with 3 layers,
Yeah.
and X1 and X2 concentrations.
Yeah.
And suppose I start with X1 equal to X2 theoretically,
right.
and introduce T-perp.
Yeah.
Can you prove that TC increases when X1 minus X2 becomes non-zero?
I mean, I can't prove anything on
No, analytically, just considering this model and then making small difference between X.
So, I mean, so certainly for the model that Erez and I looked at, where you had negative U centers with no hopping, and the metal.
This is far away.
What?
Yeah, this is far away. This is already far away. I just wanted to make the models when layers are almost identical.
Got it.
Just to make sure that TC really goes up when you move away from the like.
You know, look, if, you know, in the limit where I know how to solve this, which is in the weak coupling limit, the only thing that will matter is have I increased the density of states or decreased the density of states. You know, I could certainly set up regions where turning on T perpendicular would cause TC to go up, but it wouldn't show you anything. It's only if I get, so, you know, the starting assumption here is that I have something that wants to be a superconductor at high TC because it has pairing. Usually pairing is the hard thing. And I want to figure out a way of using that enthusiasm for good instead of evil.
Okay. Good. On this positive note, very positive note, let's go for lunch. And thanks, Steve.